Okay, now that we know how to decode using these trees, we can really think of them as being secret ciphers that we can use to encode text as a secret, and then the key to decode it is the tree. So what determines the tree in the scheme that we've used with the deck to build this thing up is the order in which the nodes are added to the deck. So the order in which the characters are added to the deck. So if I make a random sequence of characters and I add them, that's sort of my key. That'll turn into a tree. So here's if I add Y, R, T, U, O, D, W, K, blah, blah, blah. So we get a tree that looks like this. So Y, R, T, U, O, D, W, K, V, E, they all get merged first, and then other things start getting merged. Okay. So this is like my key, this tree that I just made. And it's determined from a random order of these characters. What I can do is I can use that to encode a secret message, super secret, okay? So let's look. So let's say that, so the encoded message is called a ciphertext. So I'll say that is t1.encode. Algorithms are fun. Don't tell anyone, okay? All right, so let's see what the ciphertext looks like. And let's also make sure that we can decode it now. So I'll say print t1.decode ciphertext. All right, so here's what the ciphertext looks like. Everything is kind of ones and zeros. If you tried to look that up in an ASCII table, you would get gibberish. But when we use this tree that we just created to decode it, we're able to get the message back. All right, so now let me choose another permutation of these letters. So I'll call this chars 2. So this number I'm passing along to this method getChars is just a seed for a random number generator so that I can get the same random permutation each time. It's actually called a pseudo-random sequence. It looks random, but it's actually fixed based on what number I pass in here. Okay. That's so that I can generate the same key in the future. All right, so now I'll make another tree with a different sequence of characters. Let's see what it looks like. All right, so here I had B, A, O, J, T, R, Q, G. So you see the tree looks like this. Actually, it looks exactly the same as this one. They're all going to have the exact same topology. What it means is they're all balanced trees like this. The only thing that's different, yeah, and they have the same shape. Not only are they balanced, but they're balanced where they've got all these nodes here, and then they're just not quite full over here. Because we have 28 characters, which is just shy of a power of 2. Sorry, 28, okay. But what's different here is the values in the nodes, and that actually makes all the difference if we try to go decrypt this now. So if I try to make, so now if I try to say t2.decode ciphertext, I'm going to get gibberish because that wasn't the right tree, that wasn't the right key. So that's kind of a cool application. You can use these Huffman trees to encode information, and you'll need the right key to unlock it. All right, but really, I mean, we've kind of restricted ourselves a little bit with the way that we've constructed these with the deck. They always seem to have the same shape. Do we always want them to have that shape, though? I mean, in the framework, I just said that the tree, you know, when I defined the tree, the binary Kubik tree in general, I said it's a binary tree where you got a left and a right, and only the leaves have labels associated to them. I never say anything about it having to be balanced. We liked balanced trees for binary search trees because that gave guarantees on runtime. But what if we unbalance it? So here's a tree with the same information at the root nodes. Sorry, at the leaf nodes. So all the letters are there, but it's super unbalanced. But if we look carefully, it actually kind of seems reasonable. So what I notice here is that letters that are used more frequently, like E, or a space, or R, S, N, I, O, A, T, those letters have fewer bits. So it only takes me 3 bits to get to an E, or 3 bits to get to a space. And it only takes me 4 bits to get to an R, S, N, I, O, A, or a T. It takes me a lot of bits to get down to a Q or a Z, but I don't use them very often, so it doesn't matter. All right, so this is a tree that's better suited not for encryption but for compression. If I want to use the fewest bits encoding something, then I don't want to have my tree balanced. I actually want to have things higher up that are used more frequently at higher levels because that means they'll use fewer bits. Okay, so this is called a Huffman tree. And the way that you build it is by counting the occurrence, the number of times that each character occurs that you want to put in the tree. So this doesn't just have to be from the alphabet. This can be anything that you're trying to encode, any object that you're trying to encode. But it depends on how often it shows up. That will determine how this tree is constructed. So what I did was actually went back to assignment 3, and I took our words, all of our words in the dictionary that we're using for autocomplete, and I made a loop that counted the occurrence of all the letters, weighted by the occurrences of each word. And what I got was a histogram that looked like this. So what you see is that E occurs the most often. I made the space occur at just one more often than the most occurring. But in terms of the actual counts that I got, E occurs the most often, then looks like probably T followed closely by A, I, O, N, R, and S. Okay, so those are very commonly used characters. But then J, Q, X, and Z are not used much at all. Think to your Scrabble points, how much you earn for those when you use them. So the algorithm for constructing the tree is going to change a little bit. We're not just going to merge things in whatever order they came to us. We're actually going to merge the smaller things together first. That means they'll be further down in the tree, and then the larger things later. So what we're going to do is, instead of taking 2 nodes out the front and putting them in the back of the line like we did for a deck, we're actually going to allow things to jump the line. So Q and Z are going to start off at the front. I take those both out. The sum of those is actually still should not be at the end. I mean, merging Q and Z should come out of the front of the line before anything else. So I'm going to allow the merge of Q and Z to jump to the front of the line. So I'm going to use something called a priority queue to do this. So it's also known as a heap, and we'll talk about how to implement this. Turns out this also uses a tree on the back end to implement the data structure. So we're going to use a tree to build a tree. We used a deck to build a tree before, but now we're going to use a tree called a heap to build our Huffman tree. So it just lets things jump the line. Let me just show you how this works syntactically in Python. So let's say that I had nodes. This is an empty list. So what I can say is heap push, and then a tuple actually. So I'll say, let's say maybe that Z had 2 counts. So I'll push on. So first argument is this list actually. Turns out a heap, even though it's a tree, can use a list as its underlying data structure. We'll talk about that. But anyway, so it pushes on to this list to Z. Nothing too exciting so far. Now let's push on maybe A with a count of 10. Now let's push on maybe Q only has a count of 1. So at this point, when I push this on, this should jump to the front of the line. So there's a method called Heap Pop that takes the thing out of the front of the line. So let's see what that does here. So notice that Q actually comes out first, then Z should come out, then A should come out. Okay, so as we add things, they can jump the line. And that's crucial, because we're going to want to have things come out first, which have the lowest counts, and then later merge to things that have larger counts. That's what we'll need to build this tree that's balanced as such. So I'm going to start you off with some code to do that, and you're going to finish it. And you will have constructed a Huffman tree. And that'll be it. So have fun with that, and that will conclude this module.